Hello, my name is Roy Simpson. I'm a professor of mathematics at Cosumnes River College in Sacramento, California. This lecture is for intermediate algebra. It's still a review if you're watching my review series. This review specifically is to cover graphs, not graphs of specific styles of equations like linear equations or quadratic equations or anything like that, but a general review of what a graph is and how to read graphs and data from graphs, that type of thing. The only prerequisites we really have is that you need to know everything about algebraic expressions pretty much and algebraic equations. And obviously that it implies that you should know arithmetic and all the other fun stuff. So we'll start this off with a data graph. This is real data from the United States Census Bureau. It's the number of uninsured and uninsured rate within the United States in millions from 1987 to the year 2000. Now, there's two things you should be able to do. Now, and the reason why I'm using this as my first example is because you should be able to read a graph. That's the whole point of this lecture, is to be able to kind of read a graph and interpret what the data on the graph is saying. And in this case, I'm looking at the fact that you have two different pieces of data represented on here. You have a number of an uninsured within the US, and then you have an uninsured rate. And by the way, these are health insurance. The number of uninsured is in millions, and the rates are in percents. So, for example, in 1990, there was an uninsured rate of roughly, it looks to me to be about a 13%, maybe 13.8%, somewhere around there. And in 1990, the number of people in America without health insurance was near to 35 million. Now we're going to go ahead and read a few things from this. When was the uninsured rate the highest? When was the uninsured rate the highest? So if you look through all this data set, there's two places where the uninsured rate looks to be the highest. So this lower curve right here is the uninsured rate, and it seems to me that either here or here, they're both good candidates. I'm going to say that the one on the left is slightly higher, not very much higher though, but we'll say slightly higher. So the way you read this is that you take that height and you go back down to the corresponding, what we call the input, or the year that leads to that data. If this is 1999 here, then this must be 1998, and that's just judging from the fact that the scale on the axes, and by the way, this is called the horizontal axis, and the other one is called the vertical axis. So this one right there is called the vertical axis. And it seems to me that in 1998 we had the highest uninsured rate. So I'm going to say 1998. And how many Americans were uninsured during this year? Well, the number of uninsured is represented by the graph up above. So I will go ahead and try to climb this mountain here until I get to this point right here. So it looks to me to be between 40 and 45, and in fact we'll say maybe 42.5. Now when you read that 42.5, you have to include the units of the vertical axis, and the vertical axis, the units for it are right here. Numbers are in millions, so this is 42.5 million citizens, or million people. And again, this is from the U.S. Census Bureau. And what's interesting about this is that you see that this is the highest. We're claiming that this is the year with the highest uninsured rate, but actually there are years that have higher numbers of people uninsured, and of course that's okay because there's just more people in the United States. So the rate might be the same, but if let's pretend the rate's 10% and you only have 100 people living in the country, then 10 people are uninsured. But if the rate's 10% and you have 1,000 people living in the country, then 100 people are uninsured. So same rates, but because the population is growing, so is the number of uninsured. You have to watch out for that too, because they'll say that in news reports, the number of people uninsured is growing in this country. Well, of course, because the uninsured rate is pretty level, and it's just the population is growing. That's pretty understandable. So don't be fooled by these stupid statistics and people in the news media who are willing to cite some shocking number, but in reality, it's pretty typical and expected. Does the number of uninsured Americans ever decrease during a recession? Now, the stuff that's in purple is considered to be a recessionary period. So the question is, does the number of uninsured Americans, so the number would be the upper bar, does the number of uninsured Americans ever decrease during a recession? So let's look at this first recession here, and I see the number of Americans uninsured is increasing. Second recession, it's increasing. Third recession, it's even increasing slightly. So does the number ever decrease? Nope. It's always increasing during a recession. I haven't mentioned it, but there's this little gap here. The census is taken every 10 years, and sometimes they're a little bit off, and so they make an adjustment. And so that's what this break in the graph is for, is to take into account the adjustment. Let's see, during which years did the uninsured rate decrease? So we look at the rate and we're asking between which years did it decrease? Well, I'm looking right here. There's a rate of decrease. Maybe I'll use a different color pen for this. There's a rate of decrease right here. So this region right here, we have the insurance rate decreasing. If you look, there's actually a decrease right here as well. And maybe a slight decrease also right in this region, but I don't really see a major decrease anywhere else. So it looks to me about between 1998 and maybe the year 2000, which is right there, we have a decrease. 1998 to 2000, we have a decrease in the uninsured rate. And also, let's see, if this is 2008, this must be 2007, and this must be 2006. It looks like between 2006, so I'll say, and 2006 to 2007, we also had a slight decrease in the uninsured rate, but really a very minor decrease. By the way, I should probably mention that there are quite a few other questions that can be asked about any type of graph. We can ask during which year did you have the largest rate of decrease, or maybe the largest decrease in the number of uninsured. If you're going to do that, again, by visual inspection only, I would probably say if the question was during which year did we see the largest decrease in the number of uninsured, I would probably say that would have occurred between the years 1998 and 1999. It looks like that's the steepest decline. And a similar question could be asked about the largest increase in the number of uninsured, and this might be the largest single year increase in the number of uninsured, which is 91 to 92. So there's a lot of things that can be asked when you're given a graph in mathematics. But most of this doesn't involve any type of mathematical equations. It just involves interpretation. So now we'll go ahead and go into the Cartesian coordinate system, and let's define a few things about that before we continue on into mathematics here. And what I have before you right now is a pair of axes. Now, it turns out that a long time ago, you learned to graph numbers on what was called the real number line, or the number line. You would graph 0 and 1 and 2, and you can even graph things like 1/2 and negative ones and stuff like that. And this is called the number line. It turns out that if you have a couple things you don't know, you would have two number lines. And we call the first number line, the horizontal number line, the horizontal axis. A lot of instructors and textbooks call this the x-axis, so I will also note that is known as the x-axis, but often in mathematics you don't actually use the variable x. We use t's or d's or r's or s's, so to always call it the x-axis is kind of a misnomer, so it's better to know it as the horizontal axis and this as the vertical axis, although we often call it the y-axis if that stands for the variable y. You often also draw arrows at each end because, well, this continues on and on and on forever in both directions. And of course, just like the number line that you know good old from a long time ago, this has the numbers 1, 2, 3, 4, and all the numbers in between. Okay, so it has the number 1/2 and 1/10 and 1/1,000,000th and all of that. It even has irrational numbers like the square root of 2 and any of those. And then the y-axis has the same deal: 1, 2, 3, and so on and so forth. And also down here, -1, -2, and -3. And what this allows us to do is, just like way back when you wanted to plot the number 2 on the number line, now we can plot the ordered pair 2, 3. That means over 2, up 1, 2, 3. This is the ordered pair, and I'll point at it. Ordered pair 2, 3. It's an alphabetical order, so that's x is the 2 is the x value and 3 is the y value. Okay, so you go over twice in the x direction and 3 times in the y direction. That's how you plot that point. If you wanted to plot, let's say -3, -3, you'd start at the origin and go back 1, 2, 3 and down 1, 2, 3. I just said a word I probably didn't define, so let me go ahead and define that. The center of the graph, the coordinates first of all are 0, 0 for that center, but it's also known as the origin. It's the beginning of our graph. And altogether this is known as the Cartesian coordinate system, named after Rene Descartes. I think, therefore I am. That's attributed to him. And we use this to basically find anything on a plane. Okay, so if I have a sheet of paper, I can just say go over 2 inches and up 3 inches, and that's where you'll find the letter that I want you to read or something like that. Now, the reason why we have a Cartesian coordinate system is to really kind of create a marriage between algebra and geometry. Algebra, we have equations like, well, 3x plus 6 is equal to 7 or something like that. And if you look at this, this only has one variable, so it's a one variable equation, right? And it's not that difficult to solve this. We've done this before. You subtract 6 from both sides, divide both sides by 3, ... and you'll have x is equal to 1/3. And if somebody asked you to plot that, you would plot it on a number line, because there's only one variable, so you only need to plot the one variable. Here's 0, 1/3 is probably, let's say, right here. Okay. But things change quite a bit if, for example, you're asked to graph the solution set to y equals x plus 1. In this case, solving for a variable isn't enough. You have to create a list of possibilities. And it just depends on what you want x to be. Y will depend upon it. So what is often done is people make a table of values. Now, this table of values, I'll just admit right now, will only suffice early in algebra. Later on in algebra, it'll be frowned upon if you reach for a table like this and create a table. Most instructors will actually, or should actually, mark you off for doing this. But early on in algebra, building a set of solutions using a table is absolutely fine. So let's choose some values for x. And really, you could choose anything you want for x, like a -5 if you wanted to. Well, if you let x equal a -5, then you see that y would be negative 5 plus 1, or in other words, a negative 4. You could also let x equal negative 1. If you did that, y would be a negative 1 plus 1, because I'm substituting negative 1 for x, and this would become 0. You can even let x equal 0, and you get this. Y will equal 1, and so on and so forth. If you let y equal 1, or x equal 1, y will be 2. If you let x equal 2, y will be 3. Now, this is a group of what we call ordered pair solutions to this equation. They're not the only set of solutions. There's an infinite set. Any value you can think of for x, you can plug in for x. So there's an infinite number of possibilities. However, let's go ahead and take a look at what this will look like if we graph it. And actually, I think I have a graph available here. There we go. So let's take a look at what happens when we plot these ordered pairs. So the first ordered pair I want to plot is negative 5 comma negative 4. That means I go backwards in the x direction 5 units. 1, 2, 3, 4, 5, and down 4. 1, 2, 3, 4. So it looks to me as though this point right here is one of my solutions. I'll even label that negative 5 comma negative 4. Another solution could be that we have is negative 1 comma 0. In other words, I go backwards 1, but I don't go anywhere in the y direction. So that's it. This is negative 1 comma 0 right here. Another solution is 0 comma 1. In other words, we don't go anywhere in the x direction, but we go up 1 in the y direction. That's 0 comma 1. And 1 comma 2. I'll just go ahead and put that there. And 2 comma 3. And if you notice something about these markings, if you connect them up, they form a beautiful line. Now, this is not to say that every solution to every equation will be a line. It's just that this specific equation has a very special property. We're not going to talk about it right now. I just want you to be able to elicit a pattern from a set of points. So graphing a solution set here, we set up a few points. We can see from that pattern that it should probably be that all the solutions will exist on this line. And in fact, if you plug in x equals 5, you'll get that y is equal to 5 plus 1, or 6. And so let's see if that works here. Let's go over to x equals 5 and up 6, and here we are. We're still on the graph, or on that line. So I guess that our interpretation of it, this line being a graphical representation of all the solutions to this equation, is correct. So whenever somebody says in algebra to graph the equation, they're really meaning that you're going to graph the solution set. So this is a graph of the set of solutions to the equation. This is all my shorthand, by the way. EQN is the equation, SOLNS is solutions. Now I've come over to Mathematica. This is wolframalpha.com. And in Wolfram Alpha, you can graph a lot of things and whatever, but here I've graphed the equation y equals the quantity x minus 3 squared plus 1. And I'm going to use that graph to maybe finish out some ordered pairs here. So let's use the graph of y equals x minus 3 squared plus 1 to finish out the ordered pairs. So 5 comma something. I just want to know what that something is. Well, let's go to the ordered, or to the graph here. And what I'm going to do is go over here to 5 and climb up here to C. So in other words, I'm going to plug in x equals 5. This is the x-axis, so x equals 5. I'm going to climb up to see what the corresponding output is. And it looks like, if you look over to the left here, looks like the output is going to be a 5. So I'll go ahead and use that graph to say that the output looks to be 5. The other one says, well, when the output or the y value is 2, what is the corresponding x value? So here we go. Here's the y value of 2, and I want to know what the corresponding x value is. Well, we got an issue here. At this y value of 2, you have one point on the curve, and you have another point at y equals 2 on the curve. So there are two possibilities. When x is 2, it leads to y equals 2, and when x is 4, it leads to an output of y equals 2. So you have two possibilities. Either x could be 2 or x could be 4. But they're both valid responses. Let's go ahead and check these algebraically. That's a big word to write. All right, so for the first one, it says that when we plug in 5, we should get, for x, we should get 5 out for y. Well, let's find out. Let's plug in 5 for x. Now, remember, we got that value from visual inspection, so if we're slightly off, well, it's kind of forgivable. 5 minus 3, that's a 2. 2 squared is a 4. 4 plus 1 is 5. So when we plugged in 5 for x, our y value became 5. Okay, it checked out. The other cases are not as easy because it involves a little more advanced algebra than we have at this point. But we could try it out. If you remember how to do this, then that'll be fine. Remember, we wanted the y value to be 2. And we want to know what x would correspond with that y value of 2. And we're claiming that x equals 2 will satisfy it, or x equals 4. So let's plug in x equals 2 first. So if x is equal to 2, we get, is it true that 2 is equal to, let's see, 2 minus 3 squared plus 1. Well, 2 minus 3 is a negative 1. But a negative 1 squared is just 1. And 1 plus 1 is 2. Aha. So is it true that 2 is equal to 2? Sure is. And then you could do the same thing if x is equal to 4. Well, again, we want to know, is that y value of 2 going to equal to 4 minus 3 squared plus 1? Well, 4 minus 3 is just 1 squared plus 1. And 1 squared is just 1, so that's 1 plus 1, or 2, which again checks out. So again, I want to reiterate, because it's so very, very important, that the graph of an equation, like this graph right here, this graph is only containing points that solve this equation. It only contains ordered pairs that satisfy this equation. Everything that's not on this blue curve does not satisfy that equation. So like the point 1 comma 2 does not make this equation true, but the point 3 comma 1 does, because it exists on the curve.